Okay, good morning, everybody. We now have a plenary session on future gravitational wave projects and on just ongoing or finished missions on precise measurements of gravitational effects or tests of the foundations of gravity. So the first speaker is Stefano VITALE, and he is talking about Gravitational Wave Astronomy in ESA Science Programme. Please.
Thank you very much. Okay. Here we go. Thank you very much. Thank you, the organizer. Let me thank the organizer and Remo in particular for this opportunity to tell you about the gravitational wave in the ESA in the sky. And the core of this program is obviously LISA, that you know works similar to LIGO. You can call it LIGO in space. It's 3 test masses that you range with a laser interferometer. The main difference being the sheer scale of the detector, which is million kilometer here compared to the kilometer of the ground-based detector, and the reason for and the frequency range in which it's going to operate, which is microhertz to millihertz compared to the hertz to kilohertz of ground-based. And the reason why you have to go to space for those frequencies is that because the Earth's surface is gravitationally very noisy. There is a sort of wall around a few hertz, which is called the gravitational, the Newtonian gravitational noise wall, and that prevents you to do anything significant in that frequency range. It's similar to LIGO. It's not exactly to LIGO. The principle of operation of one of this mission is that basically you send a light beam from an observer, from a satellite to another satellite, and if there is a gravitational wave in between, the receiving satellite sees the frequency oscillating. That's similar to LIGO. The serious problem you have is that many other things oscillate your satellite, and so you would see a frequency modulation even in the absence of any gravitational wave, like the radiation solar pressure, and so any difference of force on the satellite would accelerate the satellite, and so one of the basic tricks you have to do such a high precision accelerometer in space is that you have to carry with you a reference test mass, that flies inside the spacecraft, and measure the acceleration of the spacecraft relative to that test mass that behaves like your inertial reference. And if you do the things carefully, it's like sending a light beam from one test mass to the other test mass, like the satellite was not there, but now the test masses are isolated and are not noisy. The other major difference is that on ground, in Virgo and in LIGO, you send the light many times back and forth between mirrors, between the 2 test masses. You don't have this luxury in space. If you try to send a light beam and collect it, if you start with a watt, you get a few photons per second. And so the only thing you can do is to send a light beam from one satellite to the other satellite, collect at the distant satellite, and send it back in a phase-locked beam, so in a sort of laser transponder. And LISA is composed by 3 of these arms with 3 satellites at 2.5 million kilometer distance each other. And you do a very poor interferometry compared to what you do on ground. On ground you do attometer. Here you do picometer, but gravitational waves are a tidal effect, so the relative shear of the formation is of the same order of magnitude. Having a test mass flying inside the spacecraft, easy to say. It's more difficult to do. As it shows there, sooner or later your test mass will drift and hit the walls of the spacecraft. So a basic trick you have to play to do LISA is that you have to measure where the test mass is inside the satellite and push the satellite to follow the test mass so that the test mass can be free and you avoid a collision with the spacecraft. And it turns that you can put 3 of these spacecraft in 3 independent orbits. You don't need any rocket or thruster, and because of a miracle of celestial mechanics, the 3 satellites keep forming a triangle, almost stable, is stable for many, many years. And so you have a detector that goes around the sun with a yearly period, which is very important to triangulate the source and to locate the source of gravitational wave in the sky. If you get a little bit into the detail, the test mass, this clean test mass inside the spacecraft is in reality a horrible thing surrounded by many different accessories. You have to carry an optical bench to do all the interferometry, and the interferometer, as you probably have already got, is made by two different interferometers. One measures the displacement of the test mass or the acceleration of the test mass relative to the optical bench. Actually, it's the other way around. The other one measures the acceleration, send the light through a telescope to the distant spacecraft and measure the acceleration of the two spacecraft, and you reconstruct the measurement from this. I didn't start my chronometer. I must say that we followed, LISA followed, the satellite followed the test mass in the direction where you're doing the measurement. In all other direction, you have to push gently the test mass. That's the reason why the test mass, I can show you a test mass because we have flown LISA Pathfinder, fits into this box here. There are millimeters all around. There is no mechanical contact. It's surrounded by electrode to give very light electrostatic forces. So why you want to go low frequency? LIGO and Virgo are doing fantastic work. Why you want to go low frequency? The reason why you want to go low frequency is Kepler. Kepler says that far away is low, right? The farther you go, the slower you orbit. And remember that the frequency of the gravitational wave is twice the frequency of the orbit or anyhow of the motion. So if you want to measure gravitational waves from things that are large, for instance, if you have a big black hole and you want to see the merging of two big black holes, the big black holes stay separated if are at a distance that is larger than their size. And if you put the size of a black hole in the Kepler formula, you get the minimum frequency before the merging is 10 millihertz, and actually is much less than that. And so if you want to go big and big in size, you have to go low frequency. And by the way, big in size means very powerful waves, because the amplitude of the emitted wave scales with the square of the mass. And so if you go to million solar mass black holes, like the one you have in the center of the galaxies, your signal scales up and you have very powerful signals. So in this comparison between LISA and LIGO and Virgo, it's not just the scale of the detector, it's just that the mass, you explore a range of sources where the mass of the source is million or billion solar mass, and where or the sources are still stellar mass, but they are in their phase where they are very much separated, like the binary in the galaxies and so on. And I'll get a little bit into the detail. So these big black holes in the center of a galaxy, you know that now we know that basically all galaxies have a gigantic black hole. This is the motion of the star around our black hole, Sagittarius A star. We know from Hubble and many other observations that galaxies collide. And so when two galaxies collide, they form a binary black hole. They form a supermassive binary black hole, and the binary black hole merges down and finally merges into a single black hole. This is a dramatic event. Already LIGO emits, the LIGO black holes emit more energy than all the universe in the electromagnetic sector at the same time, and this is 1,000,000 times more energy. So basically you see this monster everywhere in the universe. If they happen, in the center range of this plot, 1 million solar mass, you have signal-to-noise ratio of 100 at a Z of 20 at the recombination here. And so you do very high precision general relativity. You measure the luminosity distance with 1%. You measure the sky location with sub-degree accuracy for the most intense sources. You measure the mass with very high precision. You measure the spin magnitude. You measure the spin vector even, given the precision of the signal. And so if you want to compare what you get having an observatory on ground and an observatory in sky, you get a stellar mass object for many years in a surrounding of our solar system, and you get galactic size object all over the universe up to recombination era with a very large signal-to-noise ratio. So this is the signal from LIGO. This is a simulated signal with no filter or matched filter from a pair of these black hole, 1 million solar masses, and so on. And so, for instance, to give you an impression of what the astronomer expect from this kind of observation, you can, because all these gigantic black holes sooner or later spinning down enter in the LISA frequency band, you can do a sort of cosmic stratigraphy, seeing the formation of the galaxies nowadays from the merging of the galaxies throughout the entire history of the universe, and the people have high expectation to be able to say what were the seed black holes that form the gigantic black hole nowadays. So you start from recombination, and you get to our, authentication in the room failed. That's a tragedy. So this is a favorite plot by my buddy Carsten that shows the scenario on black holes in the 30s where LISA will be up. And you see that many different observatories will look at black holes, but the central part, the major central part of this area, where this is the mass of the black hole, the merging black hole, and this is the redshift, is taken by LISA. And the title of the conference is justified by the fact that in the same time scale, ESA plans to fly also a major X-ray observatory called Athena, which is a mission that looks at the black hole probably in the same redshift range, at least for a good part of the redshift range, and the same mass range, giving a unique chance to do the astrophysics of this object at the same time in the electromagnetic sector and in the gravitational sector, and I'll come back to the importance of that. This is another interesting system that's very specific to LISA. This big black hole swallows small object, right? If you have a compact stellar mass black hole that falls into one of these big black hole, it will emit waves for 100,000 orbits, and so it will give you a map of the gravitational potential at the horizon surface. And the reason for the sound, this is obviously gravitational wave converted to sound with a factor million in frequency to make it audible from you. The reason why I give you the sound is that this would be the proof that there is an event horizon, right? That as soon as the particle falls in the event horizon, the signal disappears. And so the people are expecting to do very high precision demonstration of fundamental physics properties. I will go fast, but you know, there will be in this signal the fingerprint from deviation from Kerr metric, maybe due to the gas surrounding the black hole, and this overlaps with the possibility of seeing the X-rays emitted by this object, but could carry the fingerprint on how you deviate for general relativity if you believe this is still a possibility. And it's amazing that with the boosting of LISA that is now charging ahead, and as I will show you, the people is looking a bit more into this and has found non-zero probability to find tripole system where binary black hole falls into the major black hole, and obviously that's a fantastic opportunity for theorists. You do cosmography with gravitational waves, you do with LIGO, and you do with LISA. The reason is that from the way the frequency chirps, you can get the energy, or you can get the amplitude of the signal at the source, and so measuring the amplitude of the signal here, you range the source and get an independent measurement of the distance to the source. Unfortunately, you don't get the redshift, because the redshift is already included in the signal, but if you can get the redshift from an electromagnetic counterpart, and again, let me show you the name of Athena in all the studies that says that if there is a gas surrounding, if there is matter surrounding the black hole, you will have a powerful and detailed X-ray emission. Then if you find an electromagnetic counterpart, you can put points in this distance versus redshift equation of state of the universe. And with other sources in LISA, you can do the same even without the electromagnetic counterpart. If you have a good model of your cosmology, you can fit your signals. And so this is what the people expect to say independently of any supernova survey and so on the scale of the universe. And I think I have to speed up, right? Because it's burned 13 minutes of my time. But LISA will see now small object separated by large distance that emit a low frequency in the band. When I gave those talks before 2015, this was the big selling point of LISA. There are objects in the galaxies that we know we can calculate exactly the gravitational wave emitted. We call the verification binaries. So in the early days, I would say, even if the ground base don't detect any gravitational wave, LISA will detect these waves. Nowadays, however, LISA will do an enormous census of this binary object in the galaxies. And again, it's amazing that in the ESA Science Programme, there is flying now a mission Gaia, which is delivering the most impressive catalog of all stars in the galaxies. And you see already paper showing up discussing the statistics of white dwarf mergers. And optimistically, LISA should be able to resolve tens of thousands of this binary merging, allowing you to make a comparing with the Gaia census to make you a statistics of the visible and invisible binary in the galaxies. And the astronomer says that this is very important for the galaxy formation theory. Don't ask me a question. And again, I'll skip the fact that now the people are really also looking if LISA can detect triples. On this small object at a large distance that emit in the LISA band, one important thing, as soon as LIGO detected the binary black hole, paper appeared in the literature that showed that if LISA had been up, would have detected the binary of LIGO a year before LIGO, because a year before LIGO would have been in the Kepler phase, emitting gravitational wave visible from LISA, then would have disappeared from the LISA band a week before the detection in LIGO and reappear in the LIGO band. And there are large expectations what you can do by following this object by 6 orders of magnitude in frequency. They call multi-frequency gravitational wave astronomy, and so on and so forth, right? So if you can look the gravitational, the science requirement document and see the enormous science case of what we know. And obviously then there is what we don't know, which will be probably more than what we know. So where we are. You may know that ESA has been a believer in LISA since the first beginning, and so they decided, yes, fine, it's beautiful, but is it feasible? And so decided to invest in demonstrating that LISA was feasible already in around year 2000 with a mission called LISA Pathfinder that was finally adopted in 2004, and that's the rest of my talk, is what's the status of the implementation of LISA now. And so what was the problem that really prevented people to buy LISA at face value? You need to have these test masses in free fall. They should accelerate only because of the curvature of the space due to the... What you don't want is that the test mass accelerate for some more mundane disturbance, and you take it as a gravitational wave. So again, using the test masses, you take the big acceleration of the satellite out, but you're left with the acceleration of the test mass. So any disturbance on the test mass will mimic a gravitational wave. And the requirement in terms of differential force is pretty demanding. You have to have, this is a spectral density, you have to have the force noise to be below this line. This is 10 to the minus 14 meter per second squared. So if you use G to measure acceleration, this is femto G, right? So you have to do femto G. There is no way you can do femto G in 1G on ground. And even if you look at space missions that fly test masses, like Microscope or GRACE, the gravitational mission, Microscope, which is by far the best one, and we will hear a talk at the end of this mission, is anyhow requesting 4 orders of magnitude worse than what LISA needed. And so the question was, is it feasible at all? Fortunately, the problem is local. What kills you is the acceleration of the test mass relative to the local inertial frame. So you don't need a 2 million kilometer to test if you're able to put test masses in such a good free fall. And so the idea of LISA Pathfinder is you take out the telescope and the arm and the other satellite, and you put one LISA arm you squeeze in one satellite. And so you have 2 test masses free floating in a satellite, and you use an interferometer to measure the relative acceleration of the 2 test masses. You carry also an interferometer to play the trick of the drag-free, having the satellite following one of the 2 test masses. A limitation of the test is that you cannot follow 2 test masses at once along the same direction, and so you have to apply a little electrostatic force, which limits the test, or threatened to limit the test. It didn't, but we were lucky. So we went to the Lagrange point 1. We put 2 of these test masses in the Lagrange point 1. These are gold platinum, these sides, 2 kilos, very dense, very clean, very non-magnetic. We put an optical bench in between, will show up quickly. We're carrying all these interferometers. Everything is, the test mass is surrounded by this electrode housing with all the electrodes to apply the force. We have to carry ultraviolet light. If you float a test mass in a satellite, there is no grounding wire. And there are cosmic rays, and the test mass keeps charging up. And to discharge, you shine ultraviolet line, generate electrons, and generate a path to discharge the test mass. And this very fine and subtle test mass, you have to lock with under 20 kilos of force at launch, otherwise rattling will destroy your satellite, and then you have to release in orbit with very high precision, so you need a caging mechanism, et cetera, et cetera. So if you want to see the hardware, which is gone long ago, it's somewhere around the sun. This was the test masses. You see here the electrode housing and everything being integrated. This is anyhow an optical system, so everything has been aligned to micron level and sub-millirad level. This was successful, and you see the optical bench, which is another jewel. This is assembled with the same technique they use to assemble the suspension wire and the mirror in Professor Kajita detector, but this is now all the optical components are connected with that. Again, you need micron precision, and we got micron precision. Everything, this big chunk of metal is connected by glass, because glass is the only thing that gives you the stability required, and you may see here this, in these two simultaneous videos, in the interest of time, the two guys being assembled in the satellite, and the satellite being mounted in the fairing of a Vega launcher. And we launched it in December 2015 from Kourou in the European spaceport, as I said, on the Vega rocket. We cruised for months to go to the Lagrange point, turning on all the instruments, everything turned on. We had a major event in February after a couple of months, which is decaging the test mass and releasing into orbit, which is a second launch campaign. So the project manager is this guy with the red sweater, which is a very cool person, but the enthusiasm of being able to release the test mass in orbit was so large that he celebrated. So what were we expecting, what were we aiming at? So we had to demonstrate that LISA needs that the acceleration of two test masses below this line here. They say, well, we don't want to spend the same money as otherwise we do LISA. So they allowed us to relax the requirement by factor 10 in amplitude. And even more important, they say, we are happy with the millihertz. Testing things at the microhertz takes forever, and time is money in space, as in life. And so we had to be below this blue line here instead of being below this yellow line here. The only thing which had the same requirement as in LISA is the interferometer between the test masses. LISA needs many picometers per root hertz to say, what the hell, we are flying an interferometer, let's do. So any measurement is limited by the interferometer noise between this line here. What we were expecting, well, the error budget for LISA Pathfinder was a book, but the two major entries were the fact that you have to apply this force to keep the test mass, is something that doesn't belong to LISA. And it turns that when you apply a force with an electrical field, your voltage is noisy, and so your force is noisy. And it turns that you have to set the maximum force you want to give with your system, and the larger the setting of this force you are prepared to give, the larger is the noise. And so this was the first source. The second source is the Brownian noise. The collision, we don't have gas, we have micropascal. Still, we have a few molecules. These molecules hit the test mass, and that's the other major source of noise. This is the Brownian noise that is shared in all the field of gravitational wave. And so the prediction was these lines here, that if you combine, we were expecting to be at this line. So on March 1st, we went into operation, bang, we were on the line. Except for the interferometer that instead of doing picometer, did femtometer. It was so good that basically disappeared from the scene. It didn't limit any measurement anymore. So why we needed to apply this electric field, why we have to apply a force to the second test mass? There is a reason. The main reason is that on this test mass, this big chunk of material exerts a gravitational pull and pulls the test mass. To mitigate that, what we did is to measure the position and the weight of every single element of the spacecraft, calculate the pull of this guy on the test mass, and put a big chunk of tungsten on the other side. That's a dangerous game, you realize, because if you make it wrong, you make the problem worse, because you're very close. And so we estimated what was our uncertainty in doing this thing, and we said, well, we can do a nano-G. We compensate at 0 plus or minus a nano-G. But when we went up, we did 22.5 nano-G, right? And so we could crank down the electrical force, and as soon as we cranked down the electrical force, we went much lower than that, basically at the LISA requirement. You may notice that even this part here, which is the Brownian noise, went down, and the reason why it went down is that all the system has a hose that goes to the outside of the satellite, and the vacuum keep improving. It's like having a pump, and if you plot this level here, the Brownian noise, as a function of time, this looks one of your plot of the pressure in your vacuum system when you open the pump for the first time. So very expensive pressure gauge. And so to cut the story short, the best thing we could do at the lower temperature, lowering the pressure in the system by lowering the temperature in February 2017, we could show this, this performance here. I'm almost finished. We could show this performance here, which, as you see, is better than LISA requirement all over the place. And so if you want to have a pictorial view of what we got, the blue is a simulation of the relative acceleration of two LISA test masses due to a pair of black hole somewhere, million solar masses black hole. The red is the acceleration noise of LISA Pathfinder. To see that it's noise, you have to zoom in, right? So you see the kind of signal-to-noise ratio you get with this performance. It would not be so clean because LISA is dominated by all sorts of gravitational signals. So the look will be more noisy, but not because of the instrument, right? So we made the press. So we had a pretty good press coverage on that. The BBC is one of our supporters. So BBC also noticed that as a consequence of LISA Pathfinder, in June 2017, the Space Program Committee of ESA approved LISA. So LISA is an approved mission for the L3, for the third large slot in the program. Sadly, I was given the honor a month later to push a button and kill LISA Pathfinder, which I wouldn't call an honor, but anyhow, the work was done, the job was done, good job. And since there, LISA has gone into a phase 0 in-house study, and now, as of a month ago, 2 industrial contracts have been delivered to 2 competing contractors to do the phase A of LISA. The mission hasn't changed very much from the early LISA. Just for the connoisseurs, it's a 3-arm mission. Don't worry, it's not the 2-arm thing has gone. It's 2 million kilometers, and the payload and the complement for the time being look very similar to what we have studied over the year. Anything different could come up from phase A, but I don't think so. It's a consortium. ESA is leading. I have to admit, I didn't count, but I think it's 13 member states are providing payload element, and NASA is firmly on board with a major participation. It's still a junior partner with a major participation. There was a very strong recommendation of the mid-decadal that NASA would basically put in LISA whatever it takes for having a successful and scientific rewarding mission. This gives you the schedule. This is the phase we are in now, very accelerated phase, and we should end this phase A and B2, which in the jargon, B1 in the jargon of space missions, at this mission formulation review in 2019, at the end of 2019. So any time after 2020, this mission could be adopted. And then from adoption, it's another 10 years before you launch. What we do in between here, how fast we will adopt, that's a question of money and planning. And what the Director of Science is working to is to get enough money from the Minister of Europe to fly LISA and Athena together, whatever it takes. It will never be really together in the sense of launching together, but to advance LISA and to have then ESA playing a major role in the scenario of astrophysics in the next decade, looking at this fantastic science of the extreme universe, both in the gravitational wave sector and the sector with LISA and Athena. And I think I'm finished here. Thank you very much.
Okay, thank you very much for this nice talk. Other questions?
No. The pulsar timing array is even lower frequency, right? Yeah, I must say that the rate the people are using, not me, I'm the plumber. The rate that people are using is more counted on the collision of galaxies, on the observed radar collision of galaxies than, right? And you also have to realize that the signal-to-noise ratio we're talking here is orders of magnitude larger. So it's not a background of big black holes. It's a few tens per year, merger of million, 500,000, 10 million solar mass black holes. So really a different observation window. Did I answer?
Well, one issue with the pulsar timer is if you have a final parsec problem where they don't merge at all, that would affect your rate as well.
Yeah.
Okay, are there other questions? Yeah. Are there no more questions? Ah, okay.
You mentioned Brownian noise as pressure and Brownian noise together. And how hard was it to take care of the Brownian noise type of phenomena in order to clean up the LISA signal? How hard was that to do?
Well, the Brownian noise is expected to be limiting, but actually was limiting in LISA Pathfinder, would be sufficient for LISA, actually even better than we need. At a high frequency in the milliards, you have seen that the margin to the LISA requirement is very large. However, I must say we reached the pressure of a micropascal at the end of the mission. We think we will do better in LISA, so maybe we will not be limited by Brownian noise, but the next in line is the little actuation force we have to do to control the angular rotation of the test masses. That will show up, if we suppress the Brownian noise, that will show up next.
Okay, we have another question.
As a summary, please, what is the biggest mass of black hole detected? What is the smallest? And what is the percent of binaries in LISA and LIGO work?
If you're asking on LIGO, I cannot tell you. If you want to know what LISA could do, I think this is the plot, right? You see, depending on the distance, basically LISA could even overlap. And actually, there are studies that show that if our ground-based colleague managed to get the third generation, like ET or Voyager and so on, here there will be an overlap at similar signal-to-noise ratio, because LISA is not very sensitive. Then you go to this monster signal-to-noise ratio when you go to million. You're still sensitive almost at a billion solar masses, but then they have to be very close, which is very unlikely, right? So I think the LIGO, I wouldn't take. I feel incompetent to take the question.
Okay, further. Okay, another question.
How about the patch charge effect? You don't mention about that.
Say it again?
How about the patch charge effect?
No. Well, the patch charge effect, we published the physical review letters, which is the best outcome of that. So we have showed that what we have investigated, Professor Lowe is referring to this static fluctuation of chemical potential on the surface of conducting bodies that form patches of charge, which was a terrifying idea in the field for years and years and years. But we have shown with a torsion pendulum that these are patches of 100 millivolt of millimeter size due to contamination. They produce 100 millivolt. In space, we made a careful experiment. We found the same result. We can compensate with an electric potential and make the coupling to charge disappear. So we measure the charge noise. It's below our error budget. But there is it was a very neat study, basically redoing what we did on ground on the satellite that I think puts a firm point in the field. So it's a Physical Review Letters of 2017. LISA Pathfinder. If you look under LISA Pathfinder, you'll find it.
Okay, I think we should stop now. We thank you again very much for the nice talk.